Well, good morning, everybody. And today we're going to talk about star colours. This is a lecture that I've prepared for the Cambridge Astro Plus series, but I thought I would do a recording of it and share it with everybody. So I've got a marvellous picture here of a whole lot of stars in the Milky Way, showing their marvellous colours. We've got some bright red ones, blue ones, white ones, fainter orange ones, all sorts going on in this picture, and it makes a very lovely place to start. But perhaps we ought to consider why it is that these stars are shining at all. And the reason is because they are, in fact, hot. And I'm illustrating that with a picture of some lava over here coming out of a volcano. You can see actually different colors in the lava. You can see the really bright white areas, the less bright orange colors, and the deep reds in there. And that's telling us something about the temperature. Now, in stars, they are hot because they carry out nuclear fusion, converting hydrogen to helium in the core, and that heat eventually comes to the surface and is radiated away as the light we see. So let's just have a little think about what heat, light, and energy are really all about. Well, heat is the energy of atoms or particles moving around at high speed. The faster they're moving, the higher the temperature. The more energy they have, the higher the temperature. And slow-moving particles are cold ones. But light is a form of energy as well. The electromagnetic radiation in all its forms carries a certain amount of energy proportional to the frequency of the light. And that relates, of course, to the inverse of the wavelength. The wavelength and the frequency determine the color of the light. So red light is low energy and appears at one end of our visible spectrum there. And high energy light appears up at the blue and violet. And if we were to go even further, we would go off into the rest of the electromagnetic spectrum, go beyond violet, we would get to ultraviolet, then X-rays and gamma rays as we gradually increase the energy. And if we went to lower energies than red, we would first go into the infrared and then the microwave and radio and TV radio frequencies down there at the very long end of things, the very low energy side. But everything in the universe has a temperature, and everything, therefore, emits a certain amount of radiation and glows. So if we look at things, it's just a matter of what color they are. And the cooler they are, if they're cool things, they will glow in the infrared part of the spectrum. And if you looked at a picture of me with an infrared camera, if you happen to have magic infrared eyes, you get an image like this. You can see that my skin, my face there is radiating at a higher temperature than my hair or my clothing. And you can also actually see that my glasses there in the picture are blocking the infrared radiation. The glass in the lenses there doesn't let the infrared through. To make an infrared telescope, you either use mirrors or you have to use very special glass that will not cause that. But basically, the color of the light, the wavelength, the energy of the light is a direct representation of the temperature. So if we look at that, we've got some light bulbs here glowing at different temperatures. Starting at 1000 degrees C, you get that vague cherry red color. Go up in temperature, you get 2000, you get to red, then orange at 3000, yellow at 4000. Things go white at 6000, and at 10,000 they go to blue. Now that's rather curious. And it's because of the way that the energy distribution comes out in the light. I've got some graphs underneath there showing how there is a peak in the energy that is emitted going to the right to longer frequencies with the visible spectrum colors, red, orange, yellow, green, blue, and purple down at the bottom there. And as we have our different light bulbs, you can see that the cherry red one actually is putting most of its energy out below the visible spectrum in the infrared, and only a little bit of it makes it through into the red. That's why we just see that faint cherry red color. Then we go to the red line, and the peak has got brighter, it's moved up, and it's also moved to the right. And at each step, the peak gets taller, and the mountain moves bodily to the right to higher energy. So you get more light, and you get light of, on average, a shorter wavelength, of higher frequency, and a bluer color, until in fact the blue hot light bulb there is putting out light beyond into the ultraviolet part of the region as well, which the really cool ones really don't put much out at all there. So if we look at some stars, we've got a number of famous stars here, and they each show those different colors: the red, orange, yellow, white, and blue. Of Antares there, surface temperature around about the 3000 mark. Arcturus, a little bit hotter. The sun, 5,800 degrees, so in that yellow range of 6,000 to 5,000 that it has marked on the screen for you. Vega, in the constellation of Lyra, a white star, around about 10,000. And Spica, in Virgo, very much a blue star, with a temperature well up into the teens. They're getting on for 20,000. So a very, very hot star indeed. And they show those colors. You can see that with the naked eye. But we can relate the color and the temperature and the power output and the mass all together. So if we plot them according to their power output and their temperature, we can see that we get a nice parade here with the small red dwarf stars down there at the bottom on the left, not much power coming from them, low temperature, and then we go up through the colors again to more powerful stars, and their power relates to their mass. At least this is true for the majority of stars, the so-called main sequence stars, the ones that are burning hydrogen to helium by nuclear fusion in their cores. Things are a bit different for some other types of stars. But if we choose to put this onto a more professional looking diagram, I like this one. It's called the Hertzsprung-Russell diagram, and it combines all of these things. We have the temperature across the bottom, and this time it's the other way around with blue on the left, but it doesn't really matter. We've got blue through white, yellow, orange, and then down to the cool red dwarf stars on the right. And the luminosity, the brightness, up the left-hand side, but that also correlates with their mass, as we've already learned. So you see the main sequence stars are the ones diagonally down from top left to bottom right, going through those same colors and mass ranges. And you can see that we've got the mass numbers written on there. So at the top left there, it's saying 60 M sun, that's 60 times the solar mass. The sun is labeled there down in the center. And also labeled on there, we've got the lifetimes in green, where it says lifetime 10 to the power 7 years. So this is a very long lived star, but they get even longer as they move down to 10 to the 11 down there at the bottom right for an orange star. We'll say more about that in a moment. And then you have the peculiar oddballs, which are the giants, the supergiants up there at the top right, where something different is going on. These are older stars or more aged stars that have gone through the main sequence process, run out of ability to do nuclear fusion of hydrogen in their cores, and have changed their balance of forces, swelled up into a much larger star in terms of size, much lower density, of course, but they have gone on in some cases to start carrying out further nuclear fusion reactions with helium going to carbon and other elements further up. And then we have the dead stars, the white dwarf stars. This is what happens to sun-like stars at the end of their life. They will go through the red giant phase and then become white dwarfs. We'll see more about that in a moment as well. And they appear down towards the bottom left of the diagram. So it's a very useful way of classifying things. But if I have a little look at a slightly simplified diagram, this one here shows the time along the bottom axis, the mass or the temperature or the burn rate, because big stars live fast and die young. Big stars, massive stars, have more fuel because they have more mass, but they burn it at a tremendous rate. They burn through it much more rapidly, and that's disproportionate, so that the lifetime of the star is very much shorter. So what we have here is these columns of stars with the different colors, and each column represents a factor of 10 in lifetime. So what we have is that the largest, the deep blue star at the top there, lives for about 1 million years. That first column corresponds to 1 million years. And then it will explode as a supernova by the time you get to the second column. So I've indicated that with a little picture of the Crab Nebula there, a supernova remnant. One row below, the blue-white, slightly smaller stars, they will live 1 million and then 10 million in the second column, and then die as a supernova. So there's 2 columns for them. The white stars manage 3 columns. That's 1, 10, 100 million years before they explode. The cooler F-type yellowy white stars there, they manage 4 columns, so that's 1 billion years. 4 steps of 10 on my diagram, and then they die, but this time they don't die as a supernova. They die a more gentle death, forming what's called a planetary nebula, where they just puff off their outer layers rather than detonating as a supernova. Now, a yellow sun-like star, that will manage to go 5 columns. So that's 1 million, 10 million, 100 million, a billion, and then 10 billion years. And our sun is about halfway through that. So actually on this chart, it would be between the 4th and 5th of the yellow dots there, making its way along. And it's when it gets to 10 billion, that's it. It will run out of fuel and also form one of these exploding planetary nebulae where the outer layers are puffed off as a smoke ring in space. Now, the bottom 2 rows, we have the yellow dwarfs for the sun. We then have the orange dwarfs, where there are in fact 6 dots on my diagram. These will live 10 times longer than the sun, so they will live 100 billion years. And what you might notice is that they will live longer than the age of the universe, in fact. So no orange dwarf star has been formed and has ever run out of fuel and died yet. So I haven't put a planetary nebula there. We are not absolutely certain because we've never had a chance to observe it, but we think that that's what will happen. They will puff off their outer layers in the same process, but it's never been observed. And of course, the red dwarf stars, we've got 7 dots. They live 1 trillion years, way longer than the current age of the universe, and the same thing applies. So if you think about it, if you form a whole lot of stars in a galaxy, then the mass mix you get has a lot of small stars and a fewer big stars. It's harder for nature to make the big ones. And so we end up with this mixture, but very rapidly the big bright blue and white stars die out, detonating as supernovae, and leave behind the longer lived yellow, orange and red stars. So gradually over time, the blue color of a galaxy, dominated by the really bright light from the supermassive stars, will fade and die, and it leaves behind a yellow, orange, red mixture down at the bottom there. And so galaxy star populations gradually evolve towards becoming redder and redder, unless, of course, they're continuing to form new generations of stars. And that's true at the moment in the current universe as we observe it. Lots of new stars are being formed out in the spiral arms. So out there we see the color being blue, dominated by the real powerhouses at the top of the diagram, whereas where star formation has already gone past its peak and has slowed right down, in the core of the galaxy, things look a lot more yellow, orange and red in there as the powerful stars have gone through their life and died and no new ones been formed to replace them. So it tells us an awful lot when we see the color of a star. We kind of need to know whether it's a dwarf star, a main sequence star carrying out nuclear fusion to place it on this diagram, because as I said, the giant stars behave slightly differently, with them blowing up and swelling to this much larger size. They are less dense and the surfaces become much cooler, so we end up with these red giants in a lot of cases. And so they can be massive, but cool. And so they are rather different. However, what we should really have a look at is what are we talking about with this word colour? What is it anyway? Well, colour is an artifact of the brain, in fact. It's not actually just a measure of the wavelength of the light, the frequency, the energy of the light. If I plot a diagram here, I've got three circles overlapping, red, green, and blue, and there are, in fact, only three colours entering your eye from the screen at the moment: red, green, and blue. Where we have them overlapping, you see the yellow, magenta, and cyan, and right in the centre you see white. But there really are only three different wavelengths of light being emitted from the screen. And your brain interprets the mixture of colours as the secondary colours, or indeed if there's an equal mixture of all three primary colours that it detects, then it sees white. And so you can get all the colours that are represented on this enormous circle here, showing every possible combination of red, green, and blue in different fractions, spread out like that. But really, it is only the three colours that are leaving the screen, and our brain is then interpreting those to produce this wonderful combination. So this is all done by the eye and the brain. So let's have a little look. 550 million years ago, in the Cambrian explosion of life, when complex life first began, the eye appeared pretty rapidly. It's obviously a huge advantage to be able to see where you're going. And these guys, the trilobites, were the first creatures to be able to see and have a working eye. And they managed to therefore dominate the seas at that time for hundreds of millions of years, in fact, because this was such an advantage to them compared to all the other life forms that were around them. But we know now from biology that the eye has evolved separately, independently, quite separate, different paths have come 40 times to produce different forms of eyes. And that we know that it doesn't take actually very long to go from a simple light-sensitive patch of skin to a fully developed form of an eye. We've got the little furry squirrel there with his eye very similar to ours. We've got a nautilus there, a much more ancient creature with a simpler eye. It's a pinhole, so no lens there, just a pinhole letting the light go in and fall to the back of the eye. And then flies with their individual array of 3,000 to 6,000 compound cells that are detecting light, forming a compound eye, a completely different way of doing it. But if we look at our furry squirrel, or indeed a human eye, then we find that it's a fully evolved camera, and you can see the sort of stages that it seems that evolution takes, from a photosensitive patch connected to some nerves leading to the brain on the surface, just simply detecting that there's light on one side of the creature, not the other perhaps, to a depression, an orifice going inwards with light sensitive surfaces, and that's able to give a bit more directionality to tell whether or not the light is coming from above or below perhaps, or to the left or to the right. And then gradually that can close over and form a pinhole, as we had with the nautilus, where you have the pinhole managing to create an image of the outside world onto the light sensitive cells, and with a bundle of nerves individually catching the signals from all of those separate parts of the simple light sensitive area, the proto-retina, then you can begin to have the brain compute an image and understand what's going on. Now, the next stage obviously is to close off the hole and protect it from dirt getting in, and then indeed to form an image forming lens so that you can do a better job in low light conditions, because a pinhole doesn't let very much light through, but a lens can produce an image with an enlarged aperture and therefore be more sensitive to light. So it seems that the process seems to go through these stages, and we see this in different evolutionary branches of the family tree of life. Now, in terms of the cells that are picking up the light at the back of the eye, we have in the human eye rods and cones. There's an electron micrograph on the left there showing the tall, thin rods and the rounded cone cells there, less of them. And the human eye has a large number of these, 125 million rod cells and about 6 million of the cone cells. And they're distributed in a pattern across the back of the eye. The rod cells are very sensitive, but only pick up black and white. They detect light or no light and the level of it, and that's it. And that's great because they're very sensitive, because it doesn't matter which color the light is, they'll still work. Whereas the cone cells are specific. They have proteins in them that only pick up particular wavelengths for the 3 different primary colors. And this is where our color vision comes from and why we see 3 main colors, because we have 3 types of cone cells. So if we have a little look at the pattern that they're distributed across the back of the retina, you can see that there is a mixture of red, green and blue cone cells shown by that dotted pattern. There are a lot more red cells than green cells, and there are hardly any blue ones. This is because the energy in those blue photons that are coming into the eye is greater, and so it's easier to excite the blue cells. We don't need quite so many of them. The red cells with the low energy light need the most, and we have more of them for that reason, in order to try to balance the colors. And we also have them only at the center of the back of the eyeball. There's a particularly favorite spot called the fovea near the middle at the back, not where the optic nerve leaves. That's actually a blind spot, but the middle part of the eye has the color vision, and the rest of it is only the black and white vision. And this may be surprising because you think that you're seeing the entire image around you in color, but your brain is cheating. It's lying to you. You can see in that graph at the top there that there are hardly any cone cells anywhere but that central peak in the middle there, shown by the red spike, whereas these peripheral parts of your eye, off axis, are dominated by the black and white cone cells. And that's important for our vision, because means that we can see things moving out in the peripheral regions just by the change in light intensity. And what the brain does is then flick your eye to that movement, grabs a color image of that piece of the visual field and remembers the colors, and then stitches all the color images on top of all the black and white together to present the view that you actually think you see. And this is responsible for a lot of things like magic tricks and optical illusions, where the brain gets it wrong. So, going back to stars, one thing that's missing is there are in fact no green stars in the gamut of all of the possible colors of stars. We have red ones, orange ones, yellow ones, white ones and blue ones, but there are no green ones. And this is curious because I told you that the peak of the light moves up through the spectrum. So the question is, why doesn't it peak in the green and we see a star with a green color? Well, let's have a look at it. As we know, as we change the temperature, things move from glowing in the infrared heat radiation up. As we get them to 1,000 degrees, they go to that cherry red color. And so once they reach that and start getting enough energy to put out the red visible light, the spectrum of the light will just contain that red light. That's the peak, moving to the right on the diagram, moving to higher energies and just getting into the visible part of the spectrum. Heat it a bit more and we get some orange light comes in. The peak moves up and to the right, it gets brighter, and a little bit of the light comes out into the orange, just squeaking into the bottom end of yellow there. And so we've now got a mixture of red light and orange light. Keep going. We add some yellow, and it's just sneaking into the green there on the diagram. So we've now got a mixture of red, orange, yellow, and green photons arriving in the eye. Keep going. We add some green into the mix and just stop at the end of the blue there. So this is a star rather like the sun, perhaps, getting up to being a hotter star. We've got that higher energy green light coming in. But you've got to remember that all of the colours are still there. We've still got the red, the orange, the yellow, and the green photons all arriving into the star at the same time. So what happens is that when a star is glowing very coolly in the invisible part, perhaps a very low mass star, a brown dwarf star, something like that, it gives off infrared radiation. Get it hot enough, it glows red, and we see red. Keep going, we get red and orange, and so the brain sees those as a mixture and comes up with the answer that the star is an orangey red colour. Add some yellow into the mix. We've now got red and orange and yellow, but red and yellow add together in our brains to make more orange. So we see orange plus orange. The star is an orange star at this point, even though the highest energy photons are coming through as yellow, but they're mixed with those others. And this is the key point. When we add some green in there, now what we've got is red plus green making yellow. If you look at our overlapping circles diagram, where red and green overlap, we get yellow. And so we've actually got yellow plus a bit of orange. And so essentially this star comes out as a yellow star. So it isn't green, even though the highest energy light is green, because it's mixed with the others. Our brain sees that and tells us that the answer is yellow. And if you keep going, you get all of those colours: red, orange, yellow, green, and now blue. And now the red, the green, and the blue can be added together, and they give us white. And so when the peak of the colours go into the blue part of the spectrum, all the colours are now present. We see the star as white. And if you keep going right up to the very hot stars, you start adding in the strong blues and the violet colours, and that tinges the white colour through into the blue end of things, with the brightness being right up at the top there in the blue area of the power output. And so the star turns blue. But at no stage can you get green on its own, not mixed with the other colours. You will either get it mixed with the reds and yellows and the orange colour light and see it as yellow, or there'll be some blue there and it will move and become a white star. So sadly, we just don't get to see any green stars at all. And really, that was the point of this particular presentation. And so I hope you've enjoyed that, and we'll see you next time.